so this is Ms. Schultz. We are doing our first lesson, at home. So this is a lesson on limits. It's a preview in the unit on limits, but this is a preview of the entire course. What is calculus? What are we going to learn? I love teaching this course. Love it, love it, love it, because there's this nice, tight, just like a few things we learn, really. I mean, it's like 3 things that we're learning all year. Everything falls into these big, huge conceptual buckets, and those 3 things are tightly related. Is awesome. So, what are the 3 things we're going to learn this year? 3 big calculus topics. They're limits, derivatives, and integrals. I know you don't know what those words mean. Great. That's the purpose of the course. What are those? What are they about? How do you do stuff with them? Okay, so limits is just one 3-week unit, 3.5-week unit. And then derivatives is a few months, and then integrals is a few months. We'll switch to integrals somewhere around January, early January, somewhere around there. And yeah, so what are limits are about, this is not a formal definition, but about it getting close to, but not at, okay? So we're talking infinity, we're getting infinitely large, we're getting infinitely small. I'm talking about 1 over infinity. We're not at 0, we're just super duper close to 0. Okay, derivatives, what's a derivative? Simple enough, rate of change. My name is Schultz, but I've learned rate of change before. Then the word for that was slope. What's up with this derivatives thing? I'll tell you in a second. Why derivatives are actually different from just classic slope, but also the same. Okay, integrals. Okay, there's 2 ways to think about integrals. You can think of them as an accumulation of a rate of change. So you can see that these are related, right? This one's a rate of change and this one's accumulating that rate of change. A lot of concrete applications, you can think of it as area and volume. You might also say, hey, Ms. Schultz, I've done area and volume before, and I certainly didn't know calculus at that point. What's up with that? So, basically, for calculus, think of anything you've done in terms of rate of change in area and volume. You have found rate of change in area volume of lines or rectilinear shapes. So you found the area of rectangles, you found the slope of lines, right? You found, and then some specific things, like triangles, some specific things that did have curves, like a circle, but not any old circle, like a perfect circle, not any curve, right? It had to be exactly a circle. Same with volume, had to be exactly a cylinder, if you got exactly a cone. But what if it's a cylinder where the base is not the same as the top? Can't do it, Or what if it's a curvy cylinder? What about that? Nope, couldn't do it. So what we can do with calculus is, instead of we are going to move beyond finding slope of a line, we're going to find the slope of any curve. So lines, any old curves, we're going to find the rate of change there. Now, of course, the rate of change is going to vary at different places. We'll talk about that. But whatever you've done before with just lines, you can now do with curves. You could probably have done this one before, by the way, by just chopping off a cone anyway, but with subtraction. But you can do rate of change, area, and volume, but now with any curve, not these very specific limiting shapes. Whoa. 3 topics: limits, derivatives, integrals. Let's move on. Okay. So I got this fresh one. Just breeze through. Let's see. It's a little zoomed in. We'll deal with that. Okay. So this is actual learning. We're going to get in the nitty gritty here about a secant line becoming a tangent line. We don't know these words. That's fine. So what's a secant line? Okay, back up. So I want to find the slope at a specific point of a curve. What? Okay, so I want to find the slope like right here. That's what I'm going for. What's the slope right here? It's kind of like, it's positive, right? We're going up. Not that fast, right? It's not sort of like totally a diagonal 45-degree angle. So I'd say it's less than a slope of 1, greater than 0, right? Okay, so I want to find the slope right there at a specific point. But as we know, what have I done up until now? I found slopes of lines, and I need 2 points on a line to find slope. That's how it's always been. You need 2 points to find the slope of a line. Guess what? That's not going to change right now. We still need 2 points, okay? You know, you were taught wrong, something. Okay, so here's my second point. Now, the line that connects these 2 points is called a secant line, okay? The slope at a point, so if I were to approximate the slope at a point, like by drawing, I'd say it looks like this, okay, something like that. You know, maybe it's like up 1/3. This is called the tangent line. So my goal is to find the slope at a point. In other words, to find the slope of the tangent line, because the tangent line is at the point. I'm going to start with the secant line and then go from there, all right? Because the secant line intersects the curve at 2 points, so we can rely on our, you know, the y2 minus y1 over x2 minus x1 formula. That's the one we're going to pull out to find slope given these 2 points. All right, let's name the points so we can get our y1, y2, x1, x2. So I've named this x value x. Hey. All right. This distance to the next x value, I'm going to call it delta x, the change in x. Makes sense? Yeah? It's the change in x. So what I want you to think about now, if this is at x, and this distance is delta x, what would I call this x value? Like if this was at 2 and this delta x was 5, what would you call this? 7, right? So in variables, like think about the operation you did there between the 2 and the 5, you're going to do the same operation between x and delta x. All right, so you would call this x plus delta x. All right, so I got my x1, x2. Now I gotta get my y1, y2. This, what's this called? If this is x, I'm not just gonna call it y. I wanna reference this in my name. I'm gonna call this f of x. So given that this guy is the y value at x is f of x. So now, what would you call the y value here? Right, f of this. F of x plus delta x. If you didn't get that, no worries, it's cool, okay? Awesome, now I have 2 points. Let's name my 2 points. My first point here is x comma f of x. Ew, right? This is the x value, that's the y value. So now, what would I name my second point? What would I name my second point? The x value is x plus delta x. And the y value is f of x plus delta x. If you're thinking this notation is getting cumbersome, you're right, it feels cumbersome, but you know, we're gonna go with it. This is what we gotta do. So the slope of a line, slope equals y2 minus y1 over x2 minus x1. So like this would be x1, y1, this would be x2, y2. Yeah? Cool, check, check, check. So now, please write for me what the slope of this secant line is, you know, between these 2 points which we've named here. What's the slope of that line? All right, let's go over it. So I got y2, which is here or there, f of x plus delta x minus y1, f of x, over y2 minus y1. Yes. Okay, great. On it. So good. Now, how do I simplify this? Can stuff cancel? Yes. What stuff? Not as much as you think. Up here, nothing cancels because these are in the arguments. The x cannot cancel. Down here, there's no like grouping parentheses, so I can cancel those. Okay. And so I'm going to rewrite it since those subtract to 0. Instead of canceling, I should say they subtract to 0. But, okay. So I'm going to simplify the slope as x plus, I'm just copying over the numerator, and on the denominator is delta x. Da, 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 da. That's the slope of the secant line. Now, okay, cool. All right, so you're like, yeah, Michelle, so I just took the slope between 2 points of a line. I've done that before, but how, my guiding question, remember, is like, how do I get the slope of a curve at a point? I want the tangent line. I want 1 point, not 2. That's the whole point. I want 1 point, not 2. So how do I get from the secant line to the tangent line? Well, here's how. I'm going to take this point and I'm going to drag it closer. Okay, so let's say I do right here. You don't have to copy this to mess up your paper. Let's say I do right here. Do you see how I'm getting closer to this tangent line? Let's say I make these 2 points pretty close like that. Oh, so close. Really close. Yeah. So I'm keeping this point fixed and bringing this point closer and closer and closer until they can't be the same point. I need 2 points, but they're going to be infinitesimally close. When I say infinitesimal, that means super duper duper small, close to 0. Okay. So what if I'm looking at all these variables? Okay. As I'm getting these 2 points really close, as I'm moving this one, a few things are changing. What's happening to delta x? That's my question to you. As this point, basically this x value is going, what is happening to delta x? It's approaching a certain number. Yeah, it's approaching 0. For these to be infinitesimally close, the distance between the 2 points is super duper duper close to 0. It is not equal to 0 because then there would be 1 point. And that's a no. But it's infinitely close to 0. That is called a limit. That is called a limit. So let's formalize this. I'm just going to recopy over here the slope of the secant line, which was f of x plus delta x minus f of x over delta x. Okay, just copying that over. So, all right, for my 2 points to become 1, I want this distance, delta x, to approach 0. I need the limit, maybe watch me first because it's new notation, as delta x approaches 0, we'll get more used to this notation, okay, of my slope, f of x plus delta x minus f of x over delta x. So that is how I find the slope of a tangent line, aka how do I find the slope of a curve? Boom, that's it. That is me finding the slope of a curve. Yep. This is also going to be known. Remember how we had the three main topics: limits, derivatives, and integrals. This is the definition of a derivative. Okay, but more on that later. All right, here's some classic secant line images just to sort of show you of 2 points approaching 1 point. So here it's like the left point approaching here. So secant line, you're approaching, oh no, it is the right one going left, yeah. And then I'm taking X and bringing it over, and I'm bringing it over. So the closer the right point is dragged to the left point, it really approximates the slope at that point. This would be point A, which would be the tangent line. But yeah, these are all secant lines because they intersect the curve twice. Oh, by the way, I should have just said up front, the word secant and tangent it's just totally coincidental that those are also trig functions. Totally coincidental. It has nothing to do with trig at all. They're their own words. Okay. The last thing I want to show you is approximating area. So what we can do with calculus is, I'm going to do a little bit of this. What we can do with calculus is we can find area under a curve. What? Not just lines. It's sweet. Okay? So we got this. So how we approximate it is similarly, how we approximate, I wanted it to be in color, so that's why I'm just looking at my screen. So how we approximate it is we actually use what we know before. We have to use, linear shapes. So we're doing rectangles, okay? Obviously this would be an under approximation. It's not, but it's, we're getting there. This is like a little over, a little under. I use the midpoint of the rectangle to define the height. Pretty good. So how can I get the area exactly? Okay, I want you to think about, a couple of things. I want to think about how many rectangles I would need to get the exact area. Infinity! What? Okay. Wow. So now, if there's infinity rectangles, I will get the exact area, not an approximation, under a curve. Secondly, what's the width of each rectangle going to be super duper close to if I have infinity rectangles? I'm going to say that again. What would the width of each rectangle be approximately? It would be approaching 0. Okay, so I have, let me show you this. Yes, so here is the width. I want you to think the width of each rectangle is approaching 0. So this is again a limit. So limits are what connects, you use the idea of a limit in the definition of a derivative, okay? Because you have the distance between 2 points approaching 0, okay? And you use the idea of a limit, so it's like the limit of the width of rectangle is going to approach 0 of the sum of areas of rectangle. We're not doing the intense notation for this. Because it's overwhelming. So if the width of the rectangle goes towards 0, and you sum up the areas of all the rectangles, obviously it's a little tricky because there's infinitely many of them, then you get the area under a curve. And that is what we'll learn for the second half of the year. And that's what an integral is, okay? This is basically the definition of an integral. All right, thank you very much, and I'll see you soon. Bye.